Look at the ENIAC from 1945. This machine weighed as much as an elephant, cost millions of dollars, and required an entire room to calculate 5,000 addition problems a second. Compare that to the smartphone in your hand, which is a fraction of the cost, a fraction of the weight, and runs 16 million times more computationally powerful. This 3D scale comparison shows what that growth looks like using building blocks. If one calculation per second equals a single block, a Super Nintendo from the early 90s builds a cube that fills most of a room, but the Nintendo Switch creates a cube roughly 1.4 million times larger. Many people attribute this explosion in power to Moore's Law, the 1965 prediction that the number of transistors on a chip would simply double every 2 years. However, raw speed depends on specific physical organization. Shrinking a flawed structural design eventually hits a hard physical wall, where simply adding more parts fails to yield a faster machine. True computational leaps happen when engineers hit a severe physical bottleneck and invent an entirely new method for packaging technology. The first major roadblock was the hardware itself. Early mainframes relied on thousands of glass vacuum tubes. These generated extreme heat, took up massive amounts of space, and were notoriously fragile. Yet engineers preferred them for years because they were easy to diagnose. If a vacuum tube broke, the glass would visibly crack or turn foggy, making the failed part easy to find. Early transistors were the opposite. These point contact designs were highly sensitive to voltage spikes and prone to random failure. When broken, they looked exactly the same as the working ones, making repairs a massive headache. Scientists solved this by switching from germanium to silicon and ruling away from delicate wire leads toward flat, planar designs. The first age of computing reached its conclusion when scientists mastered transistor reliability. This allowed machines to scale into larger, more complex systems without the constant threat of hardware failure. With reliable transistors in hand, the next bottleneck was interconnection. How to efficiently wire thousands of these tiny parts together in physical space. IBM solved this in 1964 with the System 360 mainframe. This introduced a standardized, swappable computer architecture. If you needed more power or memory, you simply installed an updated hardware cabinet or frame. This exploded view shows the engineering inside those cabinets, known as solid logic technology, or SLT. IBM printed wires and resistors onto a ceramic base, then mounted separate sesame seed-sized transistors on top. IBM invested heavily to mass-produce SLT, eventually controlling 70. It offered a complete 8-bit architecture for only 150 alums, making high-performance computing affordable for the first time. This single, affordable chip enabled a generation of personal computers and gaming systems, including the Apple II, the Commodore PET, and the Atari. IBM's massive investments in vertically integrated SLT production lines made it difficult for them to pivot. While they were the masters of the mainframe era, they had allowed competitors like Intel and Texas Instruments to build a significant lead in integrated circuit technology. As the industry shifted away from mainframes towards personal computers, IBM's dominance eroded. The company that once controlled 70% of the market eventually saw its share fall to less than 1%. We are seeing this pattern repeat today. The market for smartphones and laptops has matured, while the demand for specialized AI processors and massive data centers is creating the next major growth cycle in computing. History suggests that technological leadership is temporary. Staying on top requires the willingness to abandon the very architectures that created your success to meet the next era of